Hey math fans, in the last video we discussed probabilities and how to add them when you have unions of events. So recall that given two events, which we called A1 and A2, that are not necessarily mutually exclusive, we had that for event A, which was the union of those two events, the probability of A occurring was the probability of A1 plus the probability of A2 minus the probability of their intersection. And if A1 and A2 are actually mutually exclusive, that means this intersection is null, which means the probability is 0, and it gets reduced down to the more simple case. Okay, so we can really say which is going to be equal to just the probability of A1 plus the probability of A2 for A1 and A2 mutually exclusive. Okay, and we also had that if A could be written as a larger union of sets, then we had that the probability of A was the sum of all of them separately, provided they were all mutually exclusive. Okay, so really we had a sigma, we had a summation over probabilities of A sub k. Okay, for, of course, A1, A2, all the way up until maybe some other event. They're all mutually exclusive. Here's a question for you. What if you're trying to find the sum of, or what if you're trying to find the probability of a union of more than two events where the more than two events are not all mutually exclusive? Let's say you have 3 events and 2 of them could happen at the same time. Okay, so what do you do for n equals 3? Okay, so this is the case. This formula is for n equals 2. Okay, so what about for n equals 3? Okay, and I think the easiest way to do this is just to draw a picture. So that's exactly what we're going to do. We're going to draw a big old picture. And we're going to draw kind of the worst case scenario, which is that all 3 of them have some kind of intersection that's non-empty. Okay, so I'm going to draw 3 Venn diagrams. Okay, and we might call the Venn diagrams, A1, A2, and this time A sub 3 with an overall sample space. So the question is, what is the probability of A1 union A2 union A3? Okay. So what is that probability? Well, upon first glance, you just want to add them up, right? That's the natural thing to do, and I wouldn't blame you if you wanted to add that up. Okay, so let's see if we can do that. So let's presume for a second that that's going to be equal to the probability of A1 plus the probability of A2 plus the probability of A3. But as you saw for the case of n equals 2, we had to subtract some intersections, namely the intersection between A1 and A2. So let's just try this and see where this gets us. So we're going to take the probability of A1, which I guess I'll do in yellow. So I'll do this in yellow. Plus we'll do maybe the probability of A2 in red. And we'll do the probability of A3 in, say, orange. And you'll notice, oh, look, I covered everything. Yeah, well, I double and triple counted a couple things. So we need to go ahead and remove some of that to make sure that this actually makes sense. Okay, so what did I double count exactly? Well, I double counted the intersection between A1 and A2, which was this. I double counted that. If you want to go like rewatch the video really quickly, you can just count that I double counted that. So I have to subtract that off. I have to take that minus the probability of A1 intersect A2. Okay. So I'm actually going to manually subtract that off and see what that gets us. Okay, so if I subtract that off, like this, it's fine, except there's a small complication. Because actually, we only removed one of the intersections. Okay, we still have this one. Okay, so that's what we get when we just remove it once. Okay, well, we still have to remove the intersection between, say, A2 and A3. Right, A2 and A3 intersect right here, and we need to remove that as well. Okay, so, well, let's do that. Let me try not to cause too much damage here. So I'm going to remove that intersection. Okay. And the problem is, again, one of those shaded regions still remains. Okay, but the shaded region that remains is actually going to be just this area right here. Okay. All right, so now the last thing that I'm going to do is I'm going to subtract off the intersection between A1 and A3. Okay, because between A1 and A3 right here, this was double counted because that's yellow and orange. So we need to make sure to remove that. Okay, so what happens when I remove that intersection? Okay, well, I get this. And now when I shade back in the appropriate regions, there's going to be one complication. That. I actually removed the triple intersection 3 times. Okay, so now it's not shaded at all, and I need to include the intersection between all 3 events. So I'm actually going to have to manually add that back in. So I have to add in the probability of the triple intersection. Okay. Let's see, I'm going to do that in maybe this color. I have to manually add that in. All right. So we have that for 3 non-mutually exclusive events. We have that for A1, A2, A3. We have that the probability of their union is equal to all of them added together, just like we would expect. Okay. Minus the probability of the double intersections. 2 intersect A3 minus the probability of A1 intersect A3 plus the probability of the triple intersection. And that's our answer. That's the formula. Now, this notation becomes very, very cumbersome, so I'm actually going to help us out just a little bit. Okay, so when you're summing up individual probabilities, so the probability of just one single event, you're just adding all those together, I'm actually going to notate this P1, capital P sub 1. Now, when I'm subtracting, or I guess when I'm technically adding all of the probabilities of the double intersections, I'm going to label that P2. And since I'm subtracting it, I'm actually going to have to put a minus P2 right here. And then every time that I add all the triple intersections, I'm going to label that P3. Okay, so I'm going to be very, very careful about this notation going forward. Okay, so this is really the same thing as P1 minus P2 plus P3. Now let's actually define them a little bit more formally. Okay, so what is P1 going to equal? Well, P1 is going to be the sum from I equals 1 all the way to n. Let's suppose there are n different events, or in this case, n equals 3. But just arbitrarily, we're going to say P1 is equal to the sum from I equals 1 to n of P of A sub I. So this allows us to generalize for more than 3 events. Okay. P sub 2 is going to equal all of the different double intersections. Okay, so we are now summing. And now instead of I, we're going to need 2 indices. The reason is we're going to take the probability of A sub I intersect with maybe A sub j. And in this instance, we're going to go ahead and sum over all I and j such that I is less than j, and they're all going to be between 1 and n. Okay, so in the case of n equals 2, or in the case of n equals 3, this would be I and j between 1 and 3. So 1, 2, 1, 3, and 2, 3. Remember, for intersections, the order doesn't matter, but saying that I has to be less than j assures us that we're not double counting them. Okay, so we are only taking each double intersection once. Okay, so what would P3 be? Well, we can probably generalize and say, now we introduce a third index, maybe call it k, where ij and k are going to be between 1, possibly including 1, and n, possibly including n, of the probability of ai intersect aj intersect ak. I think you know where I'm going with this notation. Okay, so in general, P sub, we'll call it M, is going to equal the sum. And I can't really use I, j, and k anymore, so we're in fact going to just use maybe I sub 1, I sub 2, all the way up to I sub m. And they're all going to be between 1 and n of P sub AI1 intersect with AI2 intersect all the way intersect with A sub I sub m. Okay, so I know that sounds like overkill, right? You feel like this is ridiculous, but trust me, this is going to make the final formula look a lot better. Because what if it's more than 3 events that we're talking about? I very well don't want to have to draw a Venn diagram and figure that out. It's very, very complicated. Okay. So with this notation underway, we can finally discuss Theorem 2.2. Theorem 2.2 will say, given n events, A sub 1, A sub 2, all the way up until A sub n, not necessarily mutually exclusive. There can be overlap. We have that for A equal to just the sum, which we'll go ahead and say starts from k equals 1 to n of all the A sub k's. And we have this astounding result. We have that the probability of A, which is really the same thing as the probability of this union, this potentially cumbersome intersecting union, is given by the following. P1 minus P2 plus P3 minus P4, and so on and so forth until you're finally adding or subtracting the last one. And since it's either positive or negative, we're just going to put a plus or a minus here, P sub n. Okay, where P sub k or P sub m is exactly as I defined it above. Okay, m indicates the number of events that you're intersecting, and you're adding all the possible m-tuple intersections. Okay. Let's prove this. I'm going to tell you, I'm going to try to go as carefully as possible, but the proof might get a little tedious, so I apologize in advance. I'm going to do my best. Proof. The sketch of the proof is that we're just going to use induction. So how does induction work? Well, assume that theorem 2.2 holds. Assume it holds for any, not n events, but n minus 1 events. We're going to use that and show that it actually does hold for n events. And you can think about kind of how this is going to work. We already kind of developed a formula for just 2 events. And the 2 events that are not necessarily mutually exclusive that we're going to include will be the n minus 1 events that works with theorem 2.2, the induction step, and the 1 event that we just excluded. So we could probably, you can think, use theorem 2.1 and just connect the dots there to show the inductive step holds. All right, let's work out the details here. Then, we have that the probability of this union, where instead of at 1, we're going to go and start at k equals 2 to n of a sub k. That is going to equal the sum from k equals 2 to n of the probability of a sub k. This is what we have designated P1, except it's not P1 because we're not starting at k equals 1. Minus this sum, which maybe it's going to be k and l between 1 and n of the probability of a sub k intersect with a sub l. Okay, plus, you can kind of guess how this is going to work. K, L, and M. Probability of a sub k intersect a sub l, intersect a sub m, minus, okay, and we're just going to keep going. Just assume that that holds. That's what that means. And we also have that the probability of the full union from k equals 1 to n of a sub k. I can pinch off the first event, and I can really write this as the probability of a sub 1 union, and then the rest of this. Okay. Now remember, by, I believe it was theorem 2.1, we have a formula for this. Okay, I can scroll back up and show you the formula. It was this. We're going to use that. Okay. So we have that this has to be equal to, I'll do this in a different color. This must be equal to the probability of the first event plus the probability of the second event minus the probability of their intersection. So we have A1 intersect with this big, messy union. Sound like I'm talking about marriage or something. All these unions. Okay, so let's talk about this for a second. This is going to equal probability of A1 plus the probability of something that we can manage, right? Because we're assuming the theorem holds for the first n-1 events, or any n-1 events, minus, now this intersection is going to distribute among all the ones in this union. So we're really going to have that this is going to equal the probability of, let me do this in a different color. Well, maybe I could do it like this. So we have the probability of, I'm going to shade this part and show you that we're going to change that. This is going to equal the union k equals 2 to n of A1 intersect AK. All right? That's what it means. So anytime you have this union, essentially it kind of distributes in. So if I have like A1 intersect with A2 union A3, then I have the overall structure. I still have this union structure, but this distributes to each term, and I have A1 intersect A2 union A1 intersect A3. So it distributes in that exact way. That's something that you'll probably see on the problem set. Okay. Now, how does this help us? Well, this is actually going to be fairly important, so I'm going to go ahead and denote it by star. Okay, and now we can actually expand this out. Okay, because, and I'll label this star as well, the reason I'm denoting these by star is because we have a formula for the union of any n-1 events. It's given by this. So we can just go ahead and write it out for each of these two asterisks. And let's see what that gets us. And this is going to be kind of the painful part. So again, I apologize. So I'm going to put the equal sign over here because we're going to need a lot of room. Okay, so we're going to have the probability of A1. That checks out. As for this term, I'm going to go ahead and underline this in black. What is that going to equal? Well, it's going to equal the sum from, what did I use? K equals 2 to n of the probability of A sub k minus, and then we have, of course, the double intersection, where k and l are going to be between 2 and n. Probability of A sub k intersect with A sub l. Plus, we're going to have the triple intersection. We'll do k, l, m. Probability of k intersect al intersect am. Minus, and so on, and so forth. And then we have this last term, which I'll do in blue. Maybe try not to shade that. Okay, and this is going to be a minus sign out in front, so don't forget about that. And this is going to be minus, big parentheses here. And we have the sum from k equals 2 to n of the probability of just this event. We have just the single probabilities of A1 intersect AK. I'm just copying that down verbatim. okay, minus, now I have the sum where we'll say K and L are going to be between 2 and N of the probability of A1 intersect with AK intersect with AL, plus, and so on and so forth. And now we're essentially done. Okay, why are we done? Well, I claim that we have everything that we need. We in fact have P1 minus P2 plus P3, okay, I guess minus P4 even though I didn't have it, plus so on and so forth until we have the P sub n. Okay, let me just point out the details. You should pause the video first and see if you can verify them yourself. See if you can see a P1 up in here. See if you can find P2, etc. Okay, so where would P1 be located? Well, remember, P1 is the sum from k equals 1 to n of all of the P sub a sub k's. Well, we only have from k equals 2, but we do have this first term. So all this is going to be P sub 1. Likewise, where is our P sub 2 going to be located? Well, we have everything from 2 to n. Okay, but what about P sub 1 intersecting with stuff? Well, we have that over here. Okay, this is everything where a sub 1 intersects with everything. Okay, so I can enumerate them just a little bit if you need me to. So this is going to be, this term is going to be, A1 intersect with A2, A1 intersect with A3, and so on and so forth. And this term is going to be A2 intersect with A3, A2 intersect with A4, and so on and so forth. Okay, so we are including A1 being intersected with everything that we need. So that is the term that we have designated P sub 2. Okay, I'll just do one more. Where is P sub 3 located? Well, P sub 3 is all the triple intersections, and we are adding those. Okay, but we're still only going between 2 and n. Okay, but over here, this is the a sub 1 component. So we are including a sub 1, and since we have a negative times a negative, that cancels out to form the positive P3 term that we want. Okay, so this is going to continue until the nth combination of these intersections, and then we have the formula that we want. Okay, now, a couple of comments on this. In set theory, this is called, I'm actually just going to box this whole formula. I'm going to draw a better box. Okay, and in set theory, we actually give this a name, and we call it the inclusion-exclusion principle. Can you guess why? Because we are first including all the single events, we are excluding all the double intersections, then we're including all the triple intersections, and so on and so forth. Okay, so I think it's a really clever name, and it honestly helps me remember the formula a lot better. Okay, in the next video, we're going to continue this, and we're actually going to look at an example of how the inclusion-exclusion principle is used. Hope you found this helpful. Have a great rest of your day.